Assalamualaikum and a very good evening to Madam Annie. Today we are going to explore a fascinating topic in fluid dynamics, the formation of boundary layer and how they respond to varying airflow velocities. But first, let me introduce our team members. I'm one Annur binti Wan Abdul Halim and my metric number B1323104778 and I'm the group leader. So my part in this project are to introduce the topic, and in the video simulation assist, I'm doing the part of result until the finish of the simulation.
Hi, my name is Nurpatin Hasrini Pitasman. My metric number B1323104774. So I will talk about theory related to the topic, the problem that needs to be solved in the simulation objective, and also geometry detail and dimension.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nudratul Hikmah binti Aziz. My metric number is B1323105558. Okay, my role in this project was on the practical side. I specifically creating the geometry, configuring the simulation setup, and ensuring the accuracy in our computational model. Other than that, I'm the person in charge of sharing the relating result to the theory.
Hi, my name is Nur Shaira binti Muhammad Sahabuddin, and my metric number is 13231048 and my part in this project is explain the result presented in contour or color code and evaluating the effect.
So first is introduction to our topic. Boundary layer from when fluid flow over a surface, causing variation in velocity near the surface. Understanding this layer is essential in aerospace engineering, industrial cooling system, and optimizing aerodynamic design by reducing drag and improving the efficiency. So our project is focusing on studying how this boundary layer behave under different conditions, especially varying airflow velocities. This is not only academically interesting but also has a real-world implication for improving the performance of aerodynamic system.
The behavior of the layer. First, laminar flow. The boundary layer begins as a smooth, orderly flow near leading edge of the surface. Second, tubular flow. As the flow moves downstream, it transitions to a chaotic and unpredictable state, thickening the boundary layer. So next, problem statement. The objective is to simulate airflow over a flat plate to study the effect of a different inlet velocity on the boundary layer. Specifically, we aim to evaluate first, velocity profile at various points along the plate. Second, boundary layer thickness and how it changes with the velocity. And lastly, the relationship between theory and simulation result.
So firstly, choose fluid and click geometry, major grid spacing with 0.1 meter and minus depth per major 10 meter and snake per minor 1 meter. So next, minus depth per major 10 meter and snake per minor 1 meter. So next, draw. Choose rectangular with dimension of horizontal 1 meter and vertical 0.5 meter. And click SY plane, sketch, click concept, and click mesh, click the object, mesh, insert sizing, add edge of part of rectangular, the number of division 15, and mesh insert sizing at H2. The number of divisions is 16. And lastly, generate mesh insert sizing. The division of number 16 also. After make it H sizing of the part, create coordinate system and name as a floor.
Okay, I will continue the simulation setup process. We then need to create name selection by creating 4 coordinate system by using the edge controller. Naming each selected geometry. For the left edge, inlet. For the right edge, outlet. For the bottom surface, plane for boundary. And the top surface, far field pressure. Then, save the project. Update the mesh so it is ready for the simulation. Check on the setup. The Fluent Launcher will appear. Choose double precision to increase accuracy in all calculation. Run the simulation with only one computational core. Click on the start. Then, the Fluent software will initiate. The mesh will appear. This is the important part in computing the process. Now, we are going to set up the model. Change the configuration of the viscous model into lamina. Choose the material type as fluid air and set the air properties for density as 1 kg per meter cube and the viscosity to 1 times 10 minus 4 kg per meter second. The most crucial part is setting up the boundary condition, which will give physical meaning to the mesh. Set the inlet velocity magnitude to 1 meter per second.
So I will continue the simulation. Go to far field pressure and change type to symmetry. Next, click on method change, scheme couple to simple. Next, set solution initialization to standard initialization. Set initial velocity s equals to 1.5 meter per second, y equals to 2 meter per second. Next, set iteration to 1 million. Click calculate and watch the solution conversion. What you can see on this plot is on the x-axis you have the iteration green color code, and on the y-axis you have the solution solid conversion, that's soft purple, and last the y-axis in the residuals of each is red color code. Equation that software solving that have 3 solving equations: continuity, velocity, void equation, and void velocity.
So, I will continue about simulation in ANSYS. First, I will change the residual monitor in continuity, x velocity, y velocity in 1 x power negative 7. And I will click the calculate again. After the calculate complete, I will click the contour and I will change the contour of velocity. And it will turns out in contour of velocity magnitude graph. Then I will click the vector and I click all the airflow, far field pressure, inlet, interior airflow, outlet and plane. Then it will pop up velocity vector color by velocity magnitude graph. After that, I click the path line and I click the inlet. Then I will click the result, then click the contour 1 and I change the location into the symmetry 2 and apply. Then I go to the chart and change the x-axis to velocity u and y-axis into y. Then go to contour 1 location and change into line 1, point 1, 1, 0, 0 and point 2, 1, 0, 5 and 0. And click the chart 1, go to the location, change line 1 and apply. Then change the sample into 100. And lastly, click the vector and change the location into symmetry 2 and apply.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurratul Hikmah binti Yazid. My metric number is B132310558. Okay, my role in this project was on the practical side. I specifically creating the geometry, configuring the simulation setup, and ensuring the accuracy in our computational model. Other than that, I'm the person in charge of sharing the relating result to the theory.
Evaluating the effect. First, velocity profile. At the higher velocities, The boundary layer profile is tapered, indicating faster translation from zero velocity at the wall to the free stream velocity. Second, boundary layer thickness. Lower velocities lead to a thicker boundary layer due to the dominance of visco forces.
Okay, that's all from us. Thank you. Bye-bye.